Good evening, everybody, and we'll now start with lecture 2, wherein we are going to pick up the threads from where we left in the first lecture. So, in the first lecture, we talked about certain very basic things as to what is material science, what is the unit cell when we talk of crystal structure, the lattice planes, and few other concepts, different lattice type, revised lattices, and so on. So today we'll start with descriptive crystal chemistry. Okay. So what do I understand when I say crystal chemistry? Okay. A, it is the description or classification of structures. Then what are the factors that govern the structure that ask the material to take up that particular structure? Conditions which encourage the stability of that particular structure, and also once I have known the structure and suppose the material exhibits some property, what is the relation between the structure and the resultant physical chemical property that is exhibited by that particular material, which is of course very upcoming in the hot area in material science, to understand the correlation between the structure and property exhibited by the material, and then use that relation to design new and better materials. Okay. This one term, which is called crystallography, often it is interchanged and confused with what is crystal chemistry. Crystallography very typically refers to the experimental methods that are employed to determine the structure. So there is some subtle but very important difference between these two terms, crystal chemistry and crystallography. So with that brief thing, okay, now we have to understand different crystal structures. So what are the various ways by which I can define a crystal structure, right? I have a structure in front of me. What are the different ways by which I can understand it? One way is you can define the unit cell. And when I say you define the unit cell, means you define the shape, the size, and where exactly on what lattice points are your atoms or the lattice points situated in that particular unit cell. Second is you talk about the close packed structure. We'll talk about it a little later, cubic close packing, hexagonal close packing, distorted of these two versions, and so on. Third way is you can also define it in the form of the space filling polyhedra made by the different ions or atoms in your crystal structure. Okay, so while the first strategy, that is imagining and learning about the unit cell, gives you more accurate idea of where the atoms are placed, when we talk about the close packed structure in the space filling polyhedra, it helps us to get a better three-dimensional view of how the crystal structure is looking like. And that is why various ways are adopted to define the crystal structure, and we use any one of them as per our convenience. So talking about close packed structure, I'm sure most of you have read about it. Uh, Close packed structure, when we define what is close packing, the guiding factor in close packing is when you are trying to make or propose the close packing for the material, you have to think of the way in which achievement you can achieve maximum density. For example, and then the most efficient way of packing equal size sphere in 3 dimension. Now consider when we are talking about 2 dimension, just one plane. So what is the most efficient way of packing it? I put a sphere or a circle because I'm talking of 2 dimension. And if I'm talking of equal size circles, I can actually surround one circle by 6 circles. If you concentrate on, let's say, this particular circle, then you can pack it with 1, 2, 3, 4, 5 and 6 circles. Okay. So this is the most efficient way of packing equal sized circles in 2 dimension. So, okay, the closest neighbor in contact are, if I'm concentrating on any one particular circle, the closest neighbor in contact are 6. Okay. If you concentrate on this 2D packing, there are some interstices that you can look at. These are some triangular interstices. Okay. So there are two type of triangular interstices. One like this, which are triangles pointing upwards, and one like this, which have the triangle pointing downwards. Now I have to think of placing when I'm talking about the three dimensionality of it. Now I'll think of placing a second layer on top of it. Okay. So suppose you place second layer. Now if you just look at this, if you're talking of equal size circle, you cannot really occupy both the upper triangular interstices and the bottom downward facing triangle, because they are very close. So you can occupy only one type of interstices when you're trying to place the second layer on it. Okay, so let's say I start with placing it interstices 1. I'm talking about the upward facing triangle. Let us say that we place a second layer of identical spheres on interstices 1. So this is how it looked like. Till here, obviously, there is not much option. Now, when I talk of arranging a third layer on top of it, either you can place, now this second layer also has got two types of triangular interstices, pointing upwards and pointing downward. Now, if I again choose, if now I have to place the third layer, if I choose placing my circles in the third layer again on the first interstices, what you will observe is you will have third layer is staggered relative to both first and second layer. That is, it is a very famous arrangement that we call as ABC, ABC, ABC kind of arrangement, and this particular packing is called cubic close packing. But if you place your third layer on the interstices facing downward, let's say the second was placed on the triangular interstices facing upward, the third is placed on the interstices facing downward. What you get is your third layer of circle is directly above the first layer, which is also called as the hexagonal close packing, or the very famous arrangement of ABAB kind of packing. Okay. Coordination number in both HCP and CCP is, you just concentrate on, let's say I'm talking of this particular arrangement on right hand side bottom. If you look at any of the orange circle, it is surrounded by 6 atoms. Okay, let me go to this particular thing. If I concentrate on this particular circle, it will be surrounded by 6 atoms in the layer in which it is lying, then 3 atoms in the layer below it, and 3 atoms in the layer above it. So the coordination number in any close packing, whether it is HCP or CCP, is 12. 6 in the same layer, 3 above and 3 below. Okay. The packing density, if I want to calculate the packing density for both these, is if you are having equal size spheres and you are trying to pack them in either cubic close packing or hexagonal close packing, you will be able to occupy 74% of the space. So how we can calculate it? I'll come back to this slide once we have talked a little more about these two kind of packing. Okay. So looking at, now this was the cubic close packing. Of course, as I said, we can define the structure in terms of unit cell, in terms of close packing, and also in terms of the space filling polyhedra. That means any particular structure I should be able to view in any of the three strategies. So if I am talking of close packing, what is the unit cell of a particular close packing? Talking of HCP, it is hexagonal unit cell. This one is as of now relatively easy to understand, because your layer A is the first layer and your layer B is the second layer and layer C is the third layer. But the hexagonal close packing, the unit cell will encompass the first layer and the third layer. So this is actually the hexagonal cell, but unit cell is considered 1/3 of this. That is, if you concentrate on this particular cell, then 1/3 of this, that means if I join these two, and then this, and this parallelopipe is one unit cell. Also, you can see that the second layer that lies in between, if I am dividing this bigger hexagon into 3 unit cells, each of the atom belonging to the second layer will lie in one unit cell. So if you remember what we learned yesterday, any unit cell that contains 2 lattice points per unit cell is called the non-primitive unit cell. Now in this particular thing, if you concentrate on this unit cell, let's say this and then this parallelepiped, I have one atom lying inside it. So all these 8 atoms, 8 atoms or 8 lattice points, they contribute one, and this one lies completely in this particular unit cell, so it contributes another one. So number of the lattice point in hexagonal, in unit cell of the hexagonal close packing is 2. Okay. What is the unit cell of the cubic close packing? That is your face centered unit cell. Of course, I'll talk about it in next few slides. It is not as easy to visualize FCC units lattice or FCC unit cell in the cubic close packing. But of course, we'll try to see if we can do that. Okay. Talking about the hexagonal thing, if you look at this red figure on the bottom left, this is the 3D view. I've just chalked out 1/3 of this particular shape which is on the left top, taken 1/3 of it because that is the unit cell. The atom in the center is the second lattice point, as we said that this has 2 lattice point per unit cell. So how does it look like basically? I'm trying to look only at the basal plane, okay, this particular plane, 1, 2, 3, 4, and this atom in the center, if I want to find the coordinates of it, for your ease, it is drawn here, okay. So basically, if I try to find the coordinate of, anyway, the coordinate of these 4 lattice points or the one on the top plane would be 0, 0, 0, because it is only one lattice point. So depending on whichever I choose as the origin, I can take that as 0, 0, 0, but rest 4 also are contributing 1 by 8. So that is a single lattice point, that is 0, 0, 0. So what is the coordinate of this particular lattice point, the atom that lies here in the center? The easiest thing that I can talk about right now is, let us say, what is the z coordinate, that is half. If I take this from top to bottom atom as one lattice parameter C, then this lies at half. So z coordinate is half, okay. What is the coordinate of this particular atom that lies at the x and y coordinate? If you consider this as the origin, okay, then the lattice parameter, then the coordinate on the x axis is 1 by 3 and the coordinate on the y axis is 2 by 3, okay. So its coordinates are 1 by 3, 2 by 3, half. So what are the coordinates of the 2 lattice point in the hexagonal unit cell? 0, 0, 0 and 1 by 3, 2 by 3, half. So I hope this is clear. If this is not, I can repeat it if you type it in the chat box. Okay. Now visualizing the cubic unit cell. Okay, in hexagonal unit cell, the basal plane of the unit cell, it coincides, I'll just come back to it, Shantini. The basal plane of the unit cell, it coincides with the close packed layer, okay. That means the layers are also, your hexagonal unit cell is standing vertical. These are actually the close packed layer which form the basal plane of the unit cell, but it is not so in CCP. So these are your close packed layer in CCP. If you see that it is A, B, C and again A. But your FCC unit cell actually can be viewed in this way. Okay. So if you remember your Miller indices, you can actually see that the close packed layer, which will again become more clear in the next slide, lie along the 111 plane of the unit cell. So while the hexagonal unit cell is parallel in C direction to your close packed layer, your cubic unit cell is actually tilted so that the close packed layer are along the 111 plane or direction of your face centered unit cell, okay. And just talking about what are the 4 atoms in the face centered unit cell. So where are the 4 lattice point in the FCC cell? Corners and on the center of the 6 faces. The coordinate for the corner lattice point is 0, 0, 0, and when I talk of face, let's say one of the face would be half, half, 0, which lies on the base, then half, 0, half, and 0, half, half. So 4 lattice point, 1 coming from the corners, and all the 6 faces, they contribute half each. So 6 into 1 by 2 is 3, 1 plus 3, 4 lattice point per FCC unit cell. Just repeating how you see the coordinate of the second lattice point in the hexagonal unit cell as just requested in the chat box. Okay, so this is your hexagonal unit cell. This was the bigger cell. As I said, unit cell is the cell, is the smallest unit, that is, it is the unit, repeating unit that I select by virtue of its smallest volume and maximum symmetry. In this case, it is 1/3 of this, okay, which is represented as red figure. We're using the red balls here. So here the number of lattice points are these 8 atoms in the corner. They contribute 1. So 1 lattice point, and coordinate for that is 0, 0, 0 because it is at the corner. Now finding out the coordinate for this particular lattice point. Now one thing is very clear, that it is exactly halfway because it is AB, AB, AB kind of packing, A, B, A. So B layer is lying halfway. So Z is 1 by 2. That is very clear about this. How to find the X and Y coordinate? So this is called the projection of this. Okay. So what I have done is, basically these are your corner atoms on the plane, basal plane, and this is the atom that lies center, but lies on the basal plane, but actually it is at Z is equal to half. But we are trying to find its XY coordinate, so it has been projected on the XY plane in 2 dimension. So if you clearly look at it, this actually you can make out if you look at the close packing also, but it would be a little difficult here. So if you try to understand, just try to see what part of this is lies in the center of this circle. So it is 1 by 3 on X axis and it is 2 by 3 on Y axis. So the coordinates are 1 by 3, 2 by 3 and half. So 2 lattice point for the hexagonal close packing is 0, 0, 0 and 1 by 3, 2 by 3, half. Okay, again another representation of how you can visualize your unit cell in the close packing. So this is your hexagonal unit cell on left hand side, HCP ABA, and this is how the basal plane coincide with the base of the unit cell. But in case of CCP, these are the packing layers and this is how your FCC is drawn. So one layer, if you concentrate on the black layer, which is the B layer, and if you try to see what is the Miller indices of this plane, this is the 111 plane. So the close packed layer coincide with 111 plane of the FCC unit cell. Okay, so I hope that is little bit clear now. Now finding out what are the tetrahedral and octahedral voids. Any void that is surrounded by 4 neighboring atoms is tetrahedral. The one that is surrounded by 6 atoms is octahedral void. So in case of your close packing, let's say concentrate on the left hand side figure, you have layer A and then you have layer B. Concentrate of any atom on the layer B. So let's say this red circle, this is 1 neighboring atom and then 3 below it. Okay, that forms one tetrahedral void. Similarly, this particular atom will also contribute in the tetrahedra, now which has opposite orientation, that is the 3 atoms lying exactly above it. Okay, so one tetrahedra pointing downward, one tetrahedra pointing upward. So each lattice point contributes. So if I have n number of atom in the close packing, the number of tetrahedral holes are 2n. For each sphere, you have 2 tetrahedral voids. And how to look at the octahedral void? Okay, let's say if you look at the right hand side figure, or maybe you can look here also, if I am concentrating on this circle and this circle, and the 3 green circle lying below it, the one in the center here is the octahedral hole. Okay, for in the close packing, for every sphere we have 1 octahedral hole and 2 tetrahedral hole. n spheres, n octahedral hole and 2n tetrahedral hole. Okay. In case of cubic close packing, which is FCC unit cell, the octahedral hole, they lie at the body center and the edge centers. Okay. You can visualize it when you look at close packing also, but in case of cubic close packing, it becomes a little difficult. So it is easier to imagine it in terms of FCC unit cell. The octahedral hole lies at the center of the cube and the edge centers. And the tetrahedral holes they lie in the 8 octants in the cube. Now what are the 8 octants? Imagine a dice, the one that we use to play the board games. Divide it in the horizontally along the horizontal plane, and then vertical plane, and then the plane along the y-axis. You will get 8 small cubes. Center of each of those cube is actually the tetrahedral hole. So again, FCC unit cell means how many lattice points do I have? 4. One contributed by the corner points, and then 3 contributed by the lattice sites at the face centers. So I have 4 lattice point in the FCC unit cell. By virtue of whatever we discussed a little while earlier, 4 lattice point means 4 octahedral hole, that is 1 at the body center, and then there are 12 edges. So 12, and then each edge, if you imagine, if you visualize, contributes to 4 cube. So how many voids are contributed by 12 edges to one particular cube? 12 into 1 by 4, that is 3. So 3 by edge centers, 1 at the body center. 4 lattice point, 4 octahedral hole. 4 lattice point, 8 tetrahedral holes. Okay. So I hope this is also clear. Now this is again a very simple an attempt because how you can visualize, because you also have to give the coordinates to your tetrahedral and octahedral hole. It is easier to do it in cubic close packing because you can relate it to the face centered unit cell. But in hexagonal close packing, you need a little imagination to assign coordinates to your octahedral and tetrahedral holes. So what I'll do is, for 5 to 7 minutes, I'll make an attempt to make you understand these coordinates. If you still can't, we'll come back to it at the end of this class or at the end of next class. Okay. So let us talk about octahedral holes first. Okay. Look at this particular unit cell. As I said, the lattice point in ions means you just for now you consider that is the lattice point. So we just talked about it two slides ago, that lattice points are 0, 0, 0 and 1 by 3, 2 by 3 half. Okay. Now this was this atom. Consider this particular atom, and I am considering this 1 by 3rd as the unit cell. Okay. Now this B layer 1, 2 and 3, this forms the top, let's say assume top of the octahedra, and 1, 2 and 3, this forms the bottom of the octahedra. So this is your octahedral hole. One here, and again these 3 atoms in the B layer, they contribute to the octahedral hole with the layer on the top. So 1, 2, 3 and 1, 2, 3. In fact, this particular octahedra is shown also by joining the edges of the octahedra. Okay. Now, if I try to assign coordinates to it, just be with me. I will go very slow. I hope you understand. Otherwise, we'll repeat it. Now, this was my lattice atom. Okay. Now, this lattice atom, we decided, that time we understood that its coordinates are 1 by 3, 2 by 3, half. Okay. Now, I'm sorry, just a little issue with the cursor because I can't work without this. Okay. So now I have to find the x, y and z coordinate for this particular site, which is the octahedral hole in hexagonal close packing. Now if this was half, now this is 1z from this atom to this atom. So my layer B was at z is equal to half. Obviously, octahedral hole is at the center. So what is the z coordinate? That is 1 by 4. Okay. Now if this coordinate was 1 by 3, 2 by 3, this particular coordinate, if you just try to stretch your imagination a little, will be 2 by 3, 1 by 3. Okay. So the coordinate of this octahedral hole is 2 by 3, 1 by 3, 1 by 4. All right. One, and then this, since the same layer is also contributing to the octahedral hole on the top, the next octahedral hole, it lies directly above this particular octahedral hole. Now here the z coordinate is, because it is between z is equal to half to z is equal to 1. So this is z is equal to 3 by 4. Okay. And x and y are, because we decided the x and y was 2 by 3, 1 by 3 here. Now this is 2 by 3, 1 by 3. Similar for here, because it is lying directly above the octahedral hole at the bottom. That doesn't change x and y coordinate. That is 2 by 3, 1 by 3. While the z axis coordinate changes from 1 by 4 to 3 by 4. So two octahedral hole. Now one hexagonal unit cell contains two lattice points. So by virtue of the correlation between number of octahedral hole and the number of lattice point 1 is to 1, it has to have two octahedral hole, and we just established it is 1 by 2 by 3, 1 by 3, 1 by 4 and 2 by 3, 1 by 3, 3 by 4. Okay. Now imagining tetrahedra, that is a little more involved. Okay. Look at this particular cube. This again shows you the entire hexagon, and of course 1/3 of it is the hexagonal unit cell. Alright. Now the one at the center in the B layer, it forms tetrahedral hole with 3 here and 3 on the top. Okay. Now, and then what will be other tetrahedral holes in this involving this particular lattice point? The 3 in the layer B with 1 on the top here, and 3 in the layer B with 1 on the 3 in the layer B with this particular. Okay. So we have 4 tetrahedral holes, one which is shown here, one exactly inverted of this. Now this becomes the bottom vertex and this becomes the plane of the tetrahedra. The other two are these 3 with this particular atom, and then these 3 with this particular atom. So there are 2 tetrahedra that point downward and 2 tetrahedra hole that point upward. Which one are the upward? This particular one that is shown here, and the one joining 3 lattice point in the layer B with the one in the corner here. These two are pointing upward, and one with this and 3 in this is pointing downward, and 3 with this and this corner lattice point, this is pointing again downward. Okay. Now we have to look at their coordinates. Okay. So fine, please be with me. I'll come back to this entire thing again and we'll revise it in 2 minutes. But right now, just try to understand whatever I am saying. I am losing the cursor again. Okay. So let us talk about first this tetrahedral hole, the one that is shown here. Okay. Now, the thing is, I really cannot explain it without showing you the points. Okay, just give me 1 minute. We'll just pause for 2 minutes and come back. All right, so let's restart it. Let us concentrate on the tetrahedral hole that is being shown here. Okay, so uh, the coordinate for this particular lattice point was 2 by 3, 1 by 3, half. All right. Yeah. Now the tetrahedral void. Okay. Though if you go by the mathematical definition, the centroid of a tetrahedra. If I draw a vertical line from the vertex to the base, the centroid lies on 1/4. Like the centroid will divide this particular line in three portions, three equal portions. So its center of gravity would be 1/4 from the bottom vertex. Okay, so that means the tetrahedral void will be towards the downside, away from your vertex. Okay, so if I'm considering my tetrahedra like this, the tetrahedral void will lie exactly below this top vertex. So its x and y coordinate will be same as the lattice point, which will be 2 by 3, 1 by 3. Now deciding about its z coordinate. Okay. So I'll just show you one thing. Okay, just look at the z axis here. Okay, so what I have done is, because now I have to talk about, for octahedral hole it was easy because it lies exactly in terms of the z coordinate, it lies exactly between two layers A and B. But in this case, your tetrahedral void has got the center of gravity towards the basal plane. Suppose this is my z axis, I divide it into 8 equal portion. Okay, because each tetrahedra is divided into three parts. So this is 0 by 8, 1 by 8, 2 by 8, 3 by 8, 4 by 8, 5 by 8, 6 by 8, 7 by 8 and 8 by 8, which is 1. So I'm playing between 0 and 1. Now we were talking of this particular tetrahedra. Okay, now this point is the top vertex is actually 4 by 8, right? So the x and y coordinate is 2 by 3, 1 by 3, and the z coordinate would be on this line which divides it, this particular line, into four part, and the void would be at 1/4 of this dimension. So it will be 1/4 of half. 1 by 4 into half is 1 by 8. So the coordinate of the tetrahedral void that lies in this tetrahedra is actually 2 by 3, 1 by 3, 1 by 8. Repeating it again for you, we are concentrating on this tetrahedra. The tetrahedral void will lie exactly below this point, which ensures that x and y coordinate are similar to what we have for this lattice point. That is 2 by 3, 1 by 3. Now we have to decide about the z coordinate. Z coordinate of your corner atom that is forming this tetrahedra is actually half. Half means 4 by 8, and the centroid of the tetrahedra actually divides your vertical distance from vertex to basal plane into four equal parts. So it is 1 by 4. Now this entire z distance that I was talking about for this tetrahedra is half. I have to look for the z coordinate which will be closer to the base at 1/4 the distance of this. So it will be 1 by 4 into half, 1 by 8. 2 by 3, 1 by 3, 1 by 8. Once you have understood this, it is easy to understand the coordinate of the tetrahedral void which will be formed by this vertex and these three atoms. That is the inverted tetrahedra. Now they lie exactly over one another. Easy to understand. X and y coordinate will again be 2 by 3, 1 by 3. But now your z coordinate will be closer to the basal plane, which is the top plane. Okay, because it is an inverted tetrahedra. So if I go to this figure again, here it would be, the z coordinate would be 7 by 8. So the coordinate of your this particular tetrahedral void formed by this corner atom and these three atoms, 1, 2 and 3, is 2 by 3, 1 by 3, 7 by 8, as is shown here. Now looking for other two tetrahedral void, okay, which is formed by this this, okay, which are lying in 3 adjacent hexagonal unit cell and the corner atom which belong to the unit cell that right now we are concentrating on. So 1, 2, 3, again an inverted tetrahedra. So if you see that this is your vertex, so the tetrahedral void will exactly be above it. Okay, so that means its x and y coordinate will be 0, 0. Okay, and the y coordinate would be closer to your b axis, which we call as 4 by 8, and it has to be 1 by 4 below it, so 3 by 8. Again, making it more clear, this is the z coordinate of your tetrahedral void, 3 by 8, and this is the tetrahedra that I am talking about. 3 atoms in the basal, in the layer B, and 1 atom in the basal plane. So 0, 0, 3 by 8. Now we will talk of the tetrahedral void that lies exactly above it. One which is shown here, which is formed by this atom, and this atom, which lies in layer B, and this corner atom. Okay. So now again it is 0, 0, x and y because it is lying exactly above it, but now the y coordinate is closer to the basal plane, 5 by 8. That means my coordinates are 0, 0, 3 by 8, 0, 0, 5 by 8, 2 by 3, 1 by 3, 1 by 8, and 2 by 3, 1 by 3, 7 by 8, in which your 7 by 8 and 3 by 8 are the inverted tetrahedral hole. We generally define them as T minus, and 5 by 8 and 1 by 8 are the, 5 by 8 is the inverted, and 3 by 8 and 1 by 8, they are the two types which are pointing upward. So T plus, so 2T plus, 2T minus. Hexagonal unit cell has got 2 lattice points and it should have 4 tetrahedral hole, and we just determine the coordinates for 4 tetrahedral holes. Okay, so generally I don't intend to spend this much time on this particular thing, but I think it is good to stretch your imagination sometime and to understand, because that makes you feel closer to how the structures look and how the structures can be imagined. Okay, we'll talk of some very typical crystal structures here, which some of you might have done, those who have had background in solid state chemistry. The first one and probably the most common one is called the rock salt structure. Okay, now few guidelines before we talk about the structures. Most of the time, structures are defined as close packing of anions with cations occupying the holes. Why? Because anions are bigger, and that is why it is easier for the cations to go and occupy the voids. But of course, many a times, for example, in UO2, your cation is bigger than anion. In that case also, we define the structure and then we say that the cation forms the close packing. But whatever we decide, most of the time it is what is convenient to us. But once we decide that this is the reference we are talking about, then in entire crystal structure solving of that particular type, we keep our reference as constant. That is important. Okay. Having said that, let's come back to rock salt structure. It is defined as, now we will talk about all the 3 strategies that we talked about in the start of the class. How to define the structure in terms of unit cell, how to define the structure in terms of close packing, and how to define the structure in terms of space filling polyhedra. Okay, so it can be defined as face centered cubic unit cell or lattice of anions, where your anions occupying the corner, as you can see here, anions are the bigger balls, and also occupying the center of the faces. Cations occupy octahedral hole in the rock salt structure, and if you recall, we said in an FCC lattice, the FCC lattice, the octahedral hole exists in the body center and the edge centers. That is what is shown here. Of course, when it is a structure like NaCl, when you have the stoichiometry has got equal number of cation and anion, you can also describe it vice versa, and that would be perfectly fine. For example, here I am keeping my origin 000 for anion, but if you shift it and you take your origin on this cation which lies here, and then you try to make the structure, you will end up with exactly similar structure. So all on you, whatever is convenient to you. It is only a convention to define the close packing by anions and cation filling the voids. Okay, so coordinates of anions, whenever I am defining, now I am defining a unit cell, it's a face-centered unit cell. Easy for me to define the coordinate. Anions lie at the corner, that makes it 000, okay? And 3 lattice point coordinated by, contributed by 12 edges. They have got, what will be the, let's say I am assuming this as my origin. So what will be the lattice point of this particular place, this particular anion that lies at this face center? It is half, half, 0, okay? And then what about this? It is, let's say I'll come to this is half, 0, half, and this particular is 0, half, half. Okay, so this is how you define the lattice point. So you have 4 anions and you have to have 4 cations. The one at the body center is half, 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 and then you can find the coordinates of any 3 edge centers, which will be a position of your cations. Okay, now that I'm explaining it to you, I wish we could be face to face. I hope you know, and I'm sure most of you know. You never asked me that we talked about this is as half, half, 0. Then why didn't we counted this anion as half, half, 1? Why? Because see, one thing which is very clear to us is that each of this is contributing half. Okay, so we have only 3 lattice points. That is why we are counting 3. Also, always remember, when you have half, half, 0 and this is half, half, 1, if you think of a unit cell that lie exactly above it, then this lattice point will become half, half, 0. So it will be nothing but the repetition of this, okay? So when you are translating by 0 and between 0 and 1, the lattice points become similar, okay? That is why, and that is how this concept of face contributing half to the unit cell has come up, and it can be justified. Okay, important thing now. We have talked about the coordinate, we talked about the unit cell, we have talked about close packing. Okay, in terms of close packing, you can say it is cubic close packing of chloride, and your sodium is occupying octahedral voids. What about the coordination number? Whenever we talk about structure, we also define the coordination number. Alright, so if you concentrate at, let's say, this Na lying at the body center. So how many chloride it is surrounded with? 1 here, 1 here, 1 here, 1 here, 4, 5 and 6. So coordination number of sodium is 6. And what is the coordination? Okay, this was chlorine. Coordination number of chloride is 6. What about sodium? Concentrate of any one sodium that you want. No, this was sodium only. For sodium it is 6. For chloride, let's say concentrate on the corner chloride. Okay. So how many sodium around it? 1 here. Then 1 exactly on the top. Then 1 here exactly in the unit cell behind it. 1 here exactly in the unit cell on this side. So 6 again. Alright. So the coordination number of both sodium and chlorine is 6. And some of the compound that adopt this structure are NaCl, KCl, AgCl, MgO and so on. Okay, this I just tried to show this thing. Okay, in terms of space filling polyhedra, how can we see this? Alright, so let's assume this red ball is your chloride ion. It is surrounded by 8 sodium ion, 1, 2, 3, 4, 5 and 6. Okay. Now you concentrate on the sodium, the red ball which is in the center of the face. Now just try to imagine its polyhedra. It will be this, these two blue ion will be common to these two polyhedra. Then this edge, then this edge, then this edge, and then one on the top and one at the body center. So how you can visualize the NaCl structure is, It is formed by edge-sharing octahedra of NaCl6 or ClNa6. Okay, so how you can imagine is, I'll repeat again, NaCl or the rock salt structure can be visualized as edge-sharing octahedra of NaCl6 or ClNa6. Now this particular kind of strategy actually helps us to visualize a lot many things, which probably you will be able to appreciate more a little later. Calcium carbide structure. Now what happens when we twist it a little? If I talk about NaCl, AgCl, they're same. What happened when I have CaC2? Okay, so ideally by virtue of stoichiometry you can say that it is not 1:1, but we count it as 1:1 because carbide exists as anion. It is not C and C, it exists as single lattice point, single anion. And also how it changes the structure is, it also has a rock salt structure. Okay, your carbide ion occupying the face centered position, which is the corner and the center of the faces, and calcium occupying the octahedral voids, which is the edge centers and the body center. But now if you look at it, my chloride ion was more or less spherical, whereas your carbide ion is elongated. So what effect does it do is, it is carbide ion, they get aligned parallel to C axis, and your symmetry now changes from cubic to tetragonal. Why? Because the C axis is now elongated. It becomes elongated in the Z direction. C becomes greater than AB while A and B are equal, and your cubic symmetry transforms to tetragonal symmetry with the placement of ion similar to the rock salt structure. Alright. Second structure, zinc blende structure, we also call it sphalerite. Okay, now sphalerite structure, again, now here that is something that you have to, okay, here again, fine. So you have ZNS, the stoichiometry is 1:1, so absolutely no problem. You can describe the cubic, it is again cubic close packing. We are right now talking about the structure which involved FCC unit cell, FCC lattice or cubic close packing. Okay, because stoichiometric is same, stoichiometry is 1:1. Your wish whether you want to describe it as close packing of zinc ion or sulfide ion. Let us go with close packing of sulfide ion, and here now the cation, they occupy tetrahedral hole and not the octahedral hole. Okay, or if you are defining it as zinc forming the FCC, then sulfide occupy the tetrahedral hole. Or in other way, if you want to look it at the unit cell, anions are placed at the corner and the face center, and cations, if you remember, if you recall, where the tetrahedral holes they lie in the cube, at the center of 8 octants. So now your cation, that is zinc ion, will occupy alternate tetrahedral void, and the position of the zinc ion itself will look like a tetrahedra. So this is 1, this is 2 coming forward, this one again at the back, and this one again in the front. Okay, coordinates of anions are same as what was for the rock salt structure. Coordinates of cation now. Okay, let us talk of the octant. So 1/4, 1/4, 1/4 is this position. Okay, then XY coordinate remains same, you go to 1/4, no. Your Z coordinate remains same, 1/4, but here it is your Y coordinate, the Z coordinate is 1/4, but the X coordinate now is 3/4, 3/4, 3/4, 3/4. Similarly, 1/4, 3/4, 3/4, and 3/4, 1/4, 3/4. So Z coordinate for these two is 1/4, and you adjust the X and Y to make them back and forth. Similarly, you take Z coordinate fixed as 3/4, and you play with the X and Y coordinate so that they occupy alternate tetrahedra voids. In terms of space filling polyhedra, how can I view it as? Okay, Well, in that case, just concentrate on this particular cation. It is joined to 1, 2, 3 and 4. It is a tetrahedra. Now, this particular, now each of this, its anion, which is forming its tetrahedra, is linked to a separate tetrahedra. Okay. And only one is linked to one tetrahedra. That means two tetrahedra, any two consecutive tetrahedra are sharing corners. So in terms of space filling polyhedral imagination or visualization, it can be described as ZnS4 or SZn4 tetrahedra sharing corners. Okay, I hope I am clear. We'll talk about one more structure or rather two more structure and take a break. Now, which structure, which compound will adopt what structure? Suppose NaCl ZnS, right? Both of them have got 1:1 cation anion. Then how do I say, or how do these decide that they would adopt a rock salt structure or the zinc blende structure? Now there are many factors that control this particular thing, and in fact in the next lecture that will probably be able to start today, we'll talk about the factors that affect the structure. So one is, what is the difference between these two? Of course, both of them are FCC of one ion. In case of rock salt, the other one occupies octahedral holes, whereas in case of the zinc blende or sphalerite, the other ion occupies tetrahedral hole. Okay. One factor that decides whether rock salt or zinc blende is, if you have more ionicity in your compound, it will probably go for the rock salt structure. And if it is more covalent, it will favor zinc blende. And why is it so? That also we'll talk about in the next lecture. When you have ionic compounds, no, they tend to have as many neighboring atoms, oppositely charged neighboring atom as possible, because that increases the electrostatic attraction and provides more stability. So if you remember, the coordination number in rock salt was 6. The coordination number of zinc blende is 4. And of course, in terms of space filling polyhedra, rock salt is edge sharing octahedra, while your zinc blende is the corner sharing tetrahedra. So the more ionic compound like oxide and chalcogenides of alkaline earths or metal halides, they adopt rock salt structure. And the chalcogenides of beryllium, zinc, cadmium, the smaller ions which are more covalent, they adopt the zinc blende structure. And of course, the competition between these two will arise only when we are talking about the 1:1 stoichiometry of cation versus anion. Okay, cesium chloride, that's the simplest structure to imagine. So you have either anion or cation. By convention, let's take anion occupying corners, and the cation occupies the body center. Okay, now one important thing that, okay, let's first finish up what's written on the slide. This is a simple cubic lattice. It is not face center. Okay, and coordinates of the anion, there is only one anion in the unit cell that is contributed by 8 corners. So it's 0, 0, 0, and the coordinate of cation, again very simple, the body center half, half, half. And coordination number of both cation and anion is 8. And how? For you, it is easier to visualize for the central atom, that is cation. It has 8 corners. Simply also easy to visualize for any corner atom. Choose this one. So you have one here, then one in the cube back, one in the cube on that side, one in the cube at this side, and similarly 4 on the top. So each cation is also surrounded by 8 anion, and each anion is also surrounded by 8 cation. Okay. Coordination number is 8. And this you can actually define as, in terms of space sharing, space filling polyhedra, as edge sharing cubes of CsCl8 or ClCs8. Right. Now one point that I would want to discuss with you here is, many a times we ask students, and even though it is very well described in the class, many of them would describe it as a body center unit cell. Okay, but please, this is not a body center unit cell. This is a simple primitive unit cell. Why? We call it body center when the atom at the corner and atom at the body center are both same. Then we call it the BCC lattice or the body center unit cell. Here, your atom at the corner and the atom at the body center is basically, they are different. Actually, if you try to visualize, you can define it as the interpenetrating lattice of the cube of cesium and cube of chlorine. So it's simple, primitive cubic lattice. That is one point, and one point that I really wanted to emphasize here. Okay. Then one structure again based on CCP's AX2 structures. Now your stoichiometry changes from 1 is to 1 to 1 is to 2. The easiest is antifluoride, Na2O. Now, when your stoichiometry changes, then once you define your reference, that is what ion you are using to form the close packing or the unit cell, that has to be fixed. Because now they cannot interchange position, because now the stoichiometry changes, their coordination number will change depending on what position they are occupying. Alright. In case of Na2O, we say it is a FCC of oxide. That is, oxide ion are occupying corners and face center. And Na in ZNS, because you had 4 lattice point and 8 tetrahedral holes, you could occupy only 4 because the stoichiometry was 1 is to 1. Here you have 4 oxide ion in the FCC unit cell. So you have 8 tetrahedral hole, but your stoichiometry is also 2 is to 1. So all the 8 tetrahedral holes are occupied by sodium ion. Oxide ion at the corner and face center, Na plus in the all the octants. Coordinate of anion and cation now you can do. If you have any problem in this, feel free to email me and I shall be able to explain it to you. Let's talk about the coordination number, because now the situation is changes. For the AX structure, the coordination number of cation and anion were similar, same. Not so here. Coordination number of Na plus, if you look at any of the Na, of course, let us not even look at any of the Na, by virtue of the fact that it was occupying tetrahedral hole, its coordination number is 4. Okay, but let us look at oxide, that is the corner atom, and let us try to see how many Na are surrounding it. Okay, one which is here, alright, one would be in the cube at the back, one would be cube on the top, on this cube, and one in the cube on the top of the back cube. Similarly 4 here. So each oxide is surrounded by 8 Na. Okay. So now the way you describe it in terms of space sharing polyhedra, that also changes, because now your coordination number changes for cation and anion. So you can describe it as 3-dimensional network of edge sharing NaO4 tetrahedra. In zinc sulfide, it was the corner sharing ZnS4 tetrahedra. Here it is edge sharing NaO4 tetrahedra or edge and corner sharing cubes of ONA8. Okay, and this structure is adopted by oxide chalcogenide of alkaline earth metals such as Li2O, Li2Se, Na2S, potassium oxide, etc. Just give me 2 more minutes before we take the break, because the next structure is totally related, which is fluoride structure. Now why do we call it fluoride? Because this is inverse of antifluoride. Now your cation is bigger and cation forms the FCC and anion occupy the tetrahedral hole. So now I am sure you will be able to appreciate that, like your AX structure, now here you cannot interchange the position of cations and anions. Okay, and of course this structure is one of the most common structure for all of us who work in Department of Atomic Energy, because this is a structure adopted by your common fuel forms like UO2, PuO2 and so on. Okay, so we'll take a 2 minutes break here and then we'll come back. Thank you. All right. So till now, whatever structures we discussed, they were with the cubic close packing or the FCC lattice. Now let's talk about few structures with hexagonal close packing, which are another interesting class in themselves. Starting again with the easiest case, AX type, when your anion and cation have got the stoichiometry of 1:1. Okay. So first one is the nickel arsenide. Okay. So normally why we say rock salt structure, nickel arsenide structure, because they are the typical structure that actually represent a huge class of compounds, and it's easier to understand when we take these as references. Okay. Nickel arsenide, NaCl, so it is the hexagonal close pack analog of rock salt. When we say analog, it becomes easier for you to identify that and also here, unlike CCP, we will not be able to interchange the position of cation and anions. So we will talk about in terms of close packing of anions. Okay, it is hexagonal close packing of arsenic, and nickel occupies octahedral hole. I'm sorry, compare with the rock salt structure, it was CCP of chloride with sodium occupying octahedral hole. Again, because your cation is occupying octahedral hole, so the coordination number of both nickel and arsenic is 6. Now, but what is the difference then when I talk of a CCP and HCP? There has to be some difference, right? There was a stark difference in way in which the layers arranged, AB, and ABC, and so on. Okay, so the most interesting fact, I hope I have this for you here. Yeah. So if you try to see these blue balls, they are the hexagonally close packed atom, that is arsenic, and the yellow balls are the octahedral hole, which are occupied by nickel. Okay. Now for each arsenic you have to have one nickel, because for each arsenic means for each arsenic lattice point you have to have one nickel lattice point. Okay. Now the interesting thing is, because even if I don't try to understand it, don't try to look into it, the fact that you have placed nickel at octahedral void, the geometry of the arsenic ion in surrounding nickel has to be octahedra. And how does an octahedra look? Suppose you have a triangle at the base, the other triangle that is occupying the top face will be staggered as compared to the lower base. Okay, that is how the surrounding around nickel ion is. It's an octahedra. But what about the arsenic ion? Okay, so if you remember, or if you can see it here, the octahedral hole, they lie exactly above one another. Their Z code, only their Z coordinates were different. Okay, it was 2 by 3, 1 by 3, 1 by 4, and 2 by 3, 1 by 3, 3 by 4. That means now, and each arsenic is surrounded by 6 such nickels. That means the atmosphere, the coordination number of arsenic is 6 as compared to, like, similar to what nickel had. But the geometry of the atoms around arsenic is now not octahedra but trigonal pyramid. That is, two triangles are placed over each other in a very, very eclipsed form. Okay, so this is where your hexagonal close pack arrangement differ from the cubic close pack arrangement. So that means I will repeat all these things. It is a HCP analog of rock salt, wherein your anion, that is arsenic, forms the HCP packing. Nickel occupies octahedral hole. Coordination number of both nickel and arsenic are 6, but the polyhedra of nickel is octahedral and the polyhedra of arsenic is trigonal prismatic. And this kind of structure is generally adopted by sulfide, selenide, telluride of nickel, cobalt, iron. Okay, and just an interesting tidbit that I added here. Sometimes we describe phase transition using this concept. Now, of course, we are not calculating here, neither do we have time. But the metal-metal distance in HCP is smaller than in the CCP. Okay, so that is why FeO, which actually adopts the rock salt structure, if you apply pressure to this, the metal they come closer and it transforms from HCCP to HCP. Okay, so that kind of phase transition happens in case of iron oxide. Just an interesting fact that will, make you feel more interested in these kind of things. This is again, I've tried to show, this is the polyhedra of the arsenic, which you can see is a trigonal prism where the upper triangle and the lower triangle are eclipsed on each other, while this is the polyhedra of the nickel, which is occupying the octahedral hole. So the arrangement of atoms are in the form of two triangles which are staggered. That is an octahedra. Okay, Woodside structure. It is like zinc blende, ZnS. It exists in two polymorphs. One is zinc blende, which you study, wherein your one of the ions forms CCP and the other occupies alternate tetrahedral hole. Here, in this polymorph of ZnS, which is called zinc blende or Woodside, your anion forms HCP and cation again occupies tetrahedral hole only, but now again, like in CCP, it occupies alternate tetrahedral hole, because for each anion you have two tetrahedral voids, but here the stoichiometry is 1:1, so half of the tetrahedral voids are occupied by the cation. Okay. Also, if you remember, when I was telling you about the coordinates of tetrahedral hole, I told you that two tetrahedra point upward and two tetrahedra point downward. So when we say that alternate tetrahedra are occupied, only one type of tetrahedra would be occupied, either all tetrahedra pointing upward or all tetrahedra pointing downward. Okay, it is again in case of in terms of space filling polyhedra, it is the 3D network of ZnS4 or SZn4, and the arrangement of atom around both zinc and sulfur are tetrahedral. Okay, so yeah, now few commonly known few commonly known structures which are formed on HCP, but they're slightly different. Very common mineral or the oxide that we know, titanium oxide. Okay, a functionally very, very important material, shows very important functionalities. Most important of them is it's a very nice photocatalyst, and a lot of work goes on modifying it so that it can absorb in the visible region and contribute. How do we define its structure? It is a distorted hexagonal close packing of oxygen. That is, HCP is not regular now. It is somewhat distorted, and oxide ion are forming. So if I have, let's say, now titanium are half the number of anions. So that means octahedral holes are equivalent to the number of anions. So half of the octahedral sites are occupied by titanium and alternate rows are occupied. So in terms of edge sharing octahedra, it is edge sharing TiO6 infinite. It looks like infinite chains that are parallel to C axis. That is the octahedra sharing edges. They run parallel to C axis, and two such parallel chains, they are linked by their corners to form a three-dimensional network. Okay, so this is what the TiO2 structure is. CDI2. Now, there titanium was occupying alternate rows of octahedra. Okay, when I say alternate rows, I don't know whether you imagine, how do you imagine that? Since I'll just go back to this particular thing. So, do you see all these yellow are basically the octahedral holes? Okay, so when I say alternate rows means if this particular octahedral hole is occupied, then this particular would be occupied. This would be left out. Okay, this is what I want to say. But in case of this CDI2 structure, again cadmium is half the number of iodide. Iodide is forming HCP, but now your cadmium also occupies half the octahedral void only, like in case of titanium. But here it does not occupy alternate rows, but it occupies alternate layer. That means these blue balls will be iodide. This particular layer of yellow balls will be occupied by cadmium. Then this layer would be left out. And again, the layer below it will be occupied, and then again it would be left out. So what does it look like? It looks like a layered structure. Okay. So edge sharing TiO6, we'll have edge sharing TiO6 infinitely layer parallel to the AB plane because of the way their cadmium is filling the octahedral hole. And then these individual layers are held together by the van der Waals forces. They are not sharing any corner, nothing, only by the van der Waals forces. And that is why such kind of structure are can actually be exfoliated into layers because their bonding is such that and their structure is such that. So you have layers of octahedral holes filled up by cadmium, and the between the layers of octahedral holes are kept vacant. That is a CdI2 structure. Okay, CdCl2. CdCl2, like in CdI2 you had HCP of iodide, CdCl2 you have CCP of chloride. Now chloride ion, because it is a more ionic bond, okay, so it forms CCP of chloride, and cadmium occupies again half the octahedral side. Alternate layers are occupied, and of course I'm sorry I've written TiO6, but it's edge sharing CdCl6 octahedra parallel to AB plane, and it is below I've given examples of what kind of compounds can adopt this kind of structure. Okay, so this is about it. Silicate structure will do only when we have time. So what I would want to do is I can give you uh, meanwhile, when we are changing to the lecture, let us try to initiate the next lecture so that we have some link. You can ask me any question in the chat box if you want. Okay, Shantini, you're talking about the corner atom or you're talking about the atom on the top but on the face center? Face center. Okay. Face center is actually again like your corner atom only. Basically, when we talk about the coordinate, okay, not the coordination number. All right. So, I think fine. The coordinate of the atom on the top is actually its x and y will be half half, and its z coordinate would be 1. You're okay with that? Tell me okay, then I'll proceed ahead. Half of 1. Okay, now see, how many face center atoms do you have in a cube? Keep on typing fast so that I make you understand what I wanted to say at that time. How many face center atoms do we have? 6. But each of them contribute half. So the contribution from the face center lattice point should actually be 3. Alright. But we have 6 faces. Then why do we say it 3? A, we'll understand logically that it is contributing only half. But why do we say that? I wanted to make you understand the concept behind it. See, when I say it is half of 1, okay, I have one atom at half of 0. You're clear about that? What I want to say that lattice point at half of 0, which is the bottom plane, is equivalent to the lattice point at half of 1. Why? Because this half of 1 now becomes the bottom plane on the cube on the top of it. Okay. So that is how it explains the logic that we use, that each face center atom is contributing half. Because if I am considering the bottom face is contributing the Miller indices are of the plane, right? So they are actually belonging to the same family of plane. What is the Miller indices of the plane at the bottom? It is making a intercept of, let's say, it is 100, right? Yes, right? And so the plane which is exactly one lattice parameter, that is 1c, uh, above on this 100 plane is actually belonging to the same family of planes. Okay, so any lattice point, right? Suppose, okay, let me make you explain in that way. I have six faces. I will have six balls. I will not say lattice point, okay? I'll have six atoms, okay? But I can consider only three of these because the atom on the opposite faces are equivalent. From those two, I can consider only one contributing to my cube that I'm considering. Because if I'm considering the bottom plane to be contributing to my cube, then the top plane I have to give it to the cube on the top. Okay? So that is how it gives you the concept of six faces contributing three lattice points. And that is why when I say half of 0 is equivalent to half of 1. All right, or half 0 half is actually equivalent to half 0 1. Okay, so you can only take one plane in your cube of reference because the other one has to go, and that is why the concept of face center lattice atom contributing only half to a cube, or an edge center atom contributing only 1 by 4 to a cube has arises, because they are equivalent. The two opposite edges are equivalent. Two opposite faces are equivalent. Is that clear? All right, great. So we can, Rohit, please share the screen. Okay, so I think we have only 5 minutes now, and I would just want to initiate you into the next lecture, which would be very easy. In fact, throughout the 6, 7 lectures that I would take for you, I would not want you to cram anything. Just try to understand what you can, because materials chemistry is a very, very logical thing. You know, atoms and ions, they behave the way I behave. If I, okay, we'll talk about these kind of things later. So what are the factors that can influence crystal structure? Don't even think about what is the, that I need to learn. A, what is the formula of the compound? I have to see the stoichiometry, right? If the stoichiometry is 1:1 and I have, my atom has to go into octahedral hole, I know that all the octahedral holes would be occupied. If the stoichiometry is 1:2, I know that only half of the octahedral hole will be occupied, and this will be a different structure from AX. If and also if it has to go into tetrahedral hole, of course, whether it goes into octahedral hole or tetrahedral hole, now that depend upon the size of the atoms and ions, which is their absolute sizes as well as their relative sizes. Okay, now these two are the very different thing, and we'll talk about it. Sometimes for a particular stoichiometry only, if I'm talking of bigger sized atom, they adopt a different structure. But if I'm talking of smaller atom, they adopt a different structure. And this big and small is different from the relative sizes. Relative sizes means the size of the cation relative to the anion, or vice versa, which is also known as the very famous radius ratio rule. So what are the factors we talked about? Formula of the compound, that is the stoichiometry, the sizes of the atoms and ions, and the radius ratio rule. Another factor that governs what kind of structure would be adopted is bonding. Why? Because as we'll discuss later, when you have compound which are more covalent character, they do not really want to be surrounded by too many atoms or ions because they are not gaining anything. In case of ionic compound, more the neighbors, more is the friendship, more is the electrostatic attraction, and higher is the stabilization. So these are the some factor, and many times when you explain what kind of structure is adopted, you use all of these or many of these criteria to explain why this has happened, and then use that to predict the structure for the compounds that are unknown or you have come across for the first time. I think we'll wind up here. Okay, this was just to give you the flavor of what we will be doing, and let's meet on Friday. Meanwhile, as I mentioned in the last class, feel free to reach out to me if there is any doubt. If I know this, I'll answer immediately. If there is anything that I do not know, that'll be an opportunity for me, and I'll research about the question and come back to you. Okay? So, any question, just 1 minute, we'll hold on, and then we can just wrap it up for the day and meet on Friday. Okay, then, see you on Friday and good day. Thank you.